Every modern trade in the global options market relies on the assumption that risk can be neutralized through continuous trading and mathematically precise hedging. Louis Bachelier first proposed in 1900 that stock prices follow a random walk, modeling market movements using the mathematics of heat diffusion. Bachelier's arithmetic Brownian motion allowed for negative stock prices, a physical impossibility for assets with limited liability and positive nominal value. Geometric Brownian motion solves this by modeling the logarithm of the price as a random walk, ensuring that asset values remain strictly positive. This stochastic process consists of two components: a deterministic drift, representing the expected return, and a stochastic volatility term, representing market noise.
The noise is formally defined by a Wiener process, characterized by independent increments that follow a normal distribution with mean zero and variance delta t. Standard calculus fails for Brownian motion because the paths are nowhere differentiable and possess infinite total variation over any finite time interval. Ito's lemma is the stochastic counterpart to the chain rule, providing the differential of a function of a stochastic process. In stochastic calculus, the square of the change in the Wiener process is equal to the change in time, making second-order terms non-negligible. We define the value of an option as a function of both the underlying asset price and the time remaining until the contract expires.
By constructing a portfolio consisting of one option and a short position in a specific quantity of the underlying stock, risk is temporarily neutralized. This quantity is known as delta. To maintain a riskless position, the portfolio must be rebalanced continuously as the underlying asset price fluctuates. Because the hedged portfolio is riskless over an infinitesimal time step, it must earn the risk-free rate of return to prevent arbitrage opportunities. Combining these elements yields the Black-Scholes partial differential equation, which relates the option price to the asset price, time, volatility, and interest rates. The equation contains a time decay term, a convexity term related to volatility, and a drift term related to the risk-free interest rate.
Crucially, the expected return of the stock does not appear in the final equation. This implies that options can be priced in a risk-neutral world. To solve the equation for a specific derivative, we must define the payoff at maturity, which serves as the terminal boundary condition for the system. Solving the Black-Scholes equation directly is complex. We apply a change of variables to transform it into a more familiar physical model. The transformation reveals that the financial pricing problem is mathematically identical to the diffusion of heat in a one-dimensional rod. The solution is obtained by convolving the terminal payoff with the Green's function, or heat kernel, which is a Gaussian distribution.
The resulting closed-form solution for a European call option involves two cumulative normal distribution terms, denoted as n of d1 and n of d2. The factor d1 represents the sensitivity of the option price to the spot price, which is effectively the delta of the option. The factor d2 is the risk-neutral probability that the option will expire in the money, determining the likelihood of the contract being exercised. Put-call parity is a fundamental relationship, ensuring that a portfolio of a long call and a short put equals a forward contract on the asset.
The original model assumes that volatility is constant over the life of the option, yet real-world markets exhibit varying levels of price turbulence. When we back-calculate volatility from market prices, we often observe a smile shape, where out-of-the-money options have higher implied volatilities. Black-Scholes assumes returns follow a normal distribution, but empirical evidence shows that financial assets have fatter tails, meaning extreme events occur more frequently. These fat tails lead to an underestimation of the risk of market crashes, as the model treats 3 standard deviation moves as virtually impossible.
The stock market crash of 1987 highlighted these flaws, as the assumed geometric Brownian motion failed to account for sudden, massive liquidity gaps. To improve accuracy, the Heston model treats volatility itself as a stochastic process, allowing it to mean revert and correlate with price movements.
Jump diffusion models add a Poisson process to the standard Wiener process, accounting for discrete, sudden price discontinuities caused by news or shocks. Traders use partial derivatives of the option formula, known as the Greeks, to measure the sensitivity of their positions to different market variables. While delta measures the directional exposure, gamma measures the rate of change of delta, indicating how quickly a hedge must be adjusted.
Theta represents the cost of holding an option over time. All else being equal, the value of an option erodes as maturity approaches. Vega measures sensitivity to changes in implied volatility. It is highest for at-the-money options and decreases as the option moves away from the strike. Rho measures the impact of changes in the risk-free interest rate on the option price, a factor that becomes more significant for long-dated contracts. In practice, continuous trading is impossible due to transaction costs and discrete market hours, which introduces hedging error into the theoretical model. Modern quantitative finance uses implied volatility surfaces to price options, accounting for both different strike prices and varying times to expiration simultaneously.
For complex derivatives with no closed-form solution, we employ numerical methods like Monte Carlo simulations or finite difference schemes for the partial differential equations. Monte Carlo methods simulate thousands of possible price paths and average the discounted payoffs to determine the expected value under the risk-neutral measure. The Black-Scholes-Merton framework remains the foundation for all derivative pricing, turning the chaotic uncertainty of the markets into a solvable engineering problem. Modern stochastic control theory continues to evolve, incorporating machine learning and nonlinear dynamics to manage the inherent randomness of global financial systems.
Randomness can never be eliminated, but through the language of stochastic equations, it can be measured, priced, and mastered within the architecture of Wall Street.